Perfect. So I'm going to be telling you about a South Pole Telescope survey for protoclusters of galaxies that ended up being in the redshift range 4 to 7, just entirely from the selection effect of using the South Pole Telescope to look for these things, remarkably. And on the title page, I have our initial example that we found with the South Pole Telescope, SPT-2349, which has been studied in several papers. And in the next talk, Riley Hill will be telling you about this system in detail. So by way of a bit of introduction, progenitors of clusters, protoclusters are well traced in simulations where you have all the information available to you. And of course, we can sort of probe them observationally. We can find overdensities of galaxies at high redshifts. We expect at redshifts greater than 3, protoclusters are immense on the sky in the sense of all the material that's accreting, collapsing down to an established massive cluster. This has been shown directly in these beautiful degree scale Subaru narrowband Lyman alpha maps, like the one shown here for the 1549 protocluster from Kikuta et al. In the last year. And we've been also mapping that out in the millimeter, submillimeter. And you can see the structure traced in bright galaxies over these degree scales as well. And this is pretty much what expectation from simulations, like as you see here in the Muldrew 2015 simulation, you expect this degree scale infalling filamentary structure. Final clue by way of introduction, these lovely simulations from Chang in 2013 and 2017 suggested this inside-out formation of the protocluster cores. At early times, you expect to find the cores of protoclusters perhaps as signposts to the building mass, and that's a prelude to what we're effectively searching for with SPT with our arc-minute beam. We're finding these active cores at their most active time, perhaps in the early universe. So the SPT-SE was a 2,500 degree square millimeter wave survey aimed at the Sunyaev-Zeldovich clusters, cosmology, and CMB cosmology. It found clusters very efficiently from their shadows in the CMB. And with this ongoing 3G experiment, we expect sort of 10,000 SC clusters extending out to redshifts in excess of 2. For our purposes here, we've been looking at the emissive sources, the thermal sources, point sources, the majority, 90% of which are obvious gravitational lenses, galaxy-galaxy lenses, but a minority of which might be the cores of protoclusters. So if you have this bright 25 millijansky millimeter wave source, if it isn't a single gravitationally lensed galaxy, it would have an effective star formation rate well over 10,000 solar masses per year. So if it's a bunch, breaks up into a bunch of little galaxies, you expect it might be an extremely active protocluster core. So as per my title slide, we found one example early on that really jumped out in this vein. 14 ALMA galaxies were resolved in even relatively shallow observation at redshift 4.3. It was documented in a couple of papers with students of mine, Tim Miller and Riley Hill. And 33 galaxies in the very small core region of about an arc-minute were identified by ALMA, resolving most of the single dish Leboka flux. Looks like it's resolved into sort of 2 infalling clumps, brighter southern and a less bright northern, and corresponds in total to an IR luminosity of 10 to the 14. And it's, I think, the most concentrated system known still. So this is what it looked like in the SPT data on the left. And then zoomed in on the right, you can see even the SPT contours are extended beyond the 1 arc-minute beam and resolves into the structure with Leboka. In Herschel, it gets masked a bit with Inspire maps by all the foreground sources, although it does stand out as quite a red source, even if not substantially brighter than a lot of the foreground galaxies. This is the most spectacular object we found in SPT-SC, but knowing what to look for, can we find other similar systems? Well, we certainly have a handful, maybe 10, that ALMA resolves the extended Leboca source into multiple sources. There's no plausible lens galaxy or cluster group lens behind from various follow-up programs. And then deep Leboca maps of the wider field have shown a strong overdensity of red satellite galaxies. This is another student of mine, George Wang, published this paper this year. So here's 7 examples that we followed up with ALMA to date, all breaking up into multiple sources within the central Leboca resolved source. Here they are on the sky with false color spire maps. And you can see all the red dots are the gravitationally lensed emissive sources. And here are the 10 candidate protoclusters ranging in redshifts, the confirmed redshifts from 4 to 7. This is the wider field Leboca maps, and indeed they do show an excess in the counts, well above the field counts here, and then including the bright central source, they're extremely overdense. If you take out that bright central source, even the red satellite galaxies are still very overdense. So it does seem like there's evidence that there's sort of a protocluster environment in the wider 10 arc-minute field probed by Leboca. The initial ALMA follow-up of 5 of these systems shows multiple sources, and at the bottom is the 2349 source with all 33 galaxies. In the core region, there's about 20 galaxies that are well described by a sort of Gaussian distribution, and the DVDR plot shows that they're consistent with being semi-virialized and bound within a 10 to the 13 solar mass halo. And the other ones are more sparsely sampled, but aren't obviously inconsistent with this kind of central dispersion. We've looked in detail at the properties of the ALMA candidates in these systems. The first one, 2349, another student of mine, Kaya Roderman, studied in the infrared to look at the stellar masses and found that they were very similar to redshift 4 field galaxies, even some candidate quenched objects within this very dense protocluster core. But the interesting thing about this is that, again, go back to this lovely movie of this structure from Doug Renahan and his 2020 paper. So what we found is that there, in these 14 bright galaxies, there's already about 10 to the 12 solar masses of stellar mass. And then what Doug's movie shows is that those 14 galaxies have to collapse extremely quickly, no matter how you slice the phase space dimensions, the velocity and spatial dimensions of those things. And within 500 mega years, you have something that looks like a fairly well established BCG galaxy. And there's a growth of another almost factor of 2 in stellar mass. So we put this on a stellar mass of the BCG versus an M200 diagram and redshift 1 BCGs. And clearly the BCG stellar mass was already effectively in place of one of the most massive candidates that we can find at redshift 1. And just a radial profile plot shows that the stellar mass collapses down. So this is radius versus time. The half light radius or the half mass radius is this red curve. And it quickly kind of establishes a roughly 6 or 7 kiloparsec half mass radius for the BCG. So we can do this with all of the systems where we have ALMA sources resolved and IRAC and multiband photometry. And Kaya Roderman has been looking at this. So we have the same plot. And indeed, they all have certainly one kind of bright nugget and a few others with substantial stellar mass. But they span almost an order of magnitude in the already established stellar mass. And the same kind of scenario as in Doug's movie. This is where they end up with at redshift 1 in the BCG mass. We've looked at Lyman break galaxies in the fields as well. This is also work by Kaya Rudderman, where she's mapped out the LBG colors with Gemini images and then looked for candidates. Here's the 2349 system, shows a strong peak in Lyman break galaxies in the core region, and this is fairly ubiquitous in the 4 systems we've looked at so far. There's another system which is even much more dense in the center in Lyman break galaxies, SPT 0457. Thank you, Nina. So Lyman break galaxies seem to be confirming that there's also an extended distribution and certainly a central concentration of galaxies in all these systems. Just the number density on the sky, it's only 10 systems over 2,500 square degrees, but they're so luminous, approaching 10 to the 14 LIR, that they stand out as more than you expect, although the statistics are poor at these very bright levels compared to simulations like the 2017 Negrello simulation of redshift greater than 4 protocluster cores. The key results are really the very high concentration. On the left, this is a star formation rate, or 850 micron flux on the vertical axis versus enclosed area. And here's 2349. It's very concentrated compared to other known systems at high redshifts or simulations. And then the track of a growing coma cluster progenitor, it's as you would expect, or even more massive than the system. So the other systems, especially the higher redshift ones, are even more stark compared to the models. Here's the redshift 5 models compared to some of the other systems. And then in terms of the growth of the progenitor of a coma, these systems, since they're all about the same IR luminosity, if you turn that into stellar, into total mass, they stand out like a sore thumb as you go to higher redshift. So maybe we're not getting the mass right from that conversion, but they're clearly very massive progenitors. I just wanted to advertise that the 3G survey going deeper will be a very interesting domain to search for protoclusters. So in summary, the discovery of these SPT protoclusters is possible because of the synergy between this 2,500 square degree survey to find these rare systems, and then the ALMA to follow them up to figure out what's going on. Very unique systems potentially to study the earliest phases. They may be ubiquitous phase in massive cluster growth, or they may be a unique kind of early growth mode in the most massive systems. We don't know yet. But studying the most massive halos out to redshift 7 in these growing systems. I think one of the key lessons is the bright BCG, the central galaxies, are forming very early in these SPT systems, already well established in this concentration of central galaxies, and then they all collapse very quickly into what looks like a giant BCG. So I think these are great laboratories to study cluster growth in the early universe, and we're starting to investigate differences in the evolution between the cluster and field galaxies in these systems. So thank you.